Hello there, this is Shannon Gracie. We are covering section 4.3 today, which covers solving linear systems by the addition method. This is from the Blitzer Introductory and Intermediate Algebra for College Students textbook, and my name is Shannon Gracie. Here we go. Today we'll be solving linear systems by the addition method, using the addition method to identify systems with no solution or infinitely many solutions. And we also want to decide, what's our favorite way? What is the best way to solve these different systems? And it usually varies depending on how the system is set up. Oh, here we go. Let's get all warmed up. Go ahead and pause the movie and do this warm-up problem. Okay, let's see how you did. Remember how we were naming our equations? So for step 1, actually, I think I was doing it more like this, wasn't I? So for part 1, why don't we go ahead and substitute y equals negative 4x plus 2 into equation A. And this will enable us to solve for x. So we had y equals 7/2 x minus 3. And I'm plugging in negative 4x plus 2 in for that y, and that's equal to 7/2 x minus 3. So this was the substitution that occurred. Okay. And then I'm going to go ahead and subtract 2 from both sides. And then we'll get negative 4x is equal to 7/2 x minus 5. Okay. And then, I don't know, why don't we go ahead and we can go ahead and clear those fractions out if you'd like. If you multiply both sides by 2, it'll clear the fractions, but don't forget to distribute the 2 through the binomial. So this will yield a result of negative 8x is equal to 7/2 x times 2, and then minus 5 times 2. We'll get negative 8x is equal to, this 2 will divide out and we'll get 7x's minus 10. Subtracting 7x from both sides, we'll have negative 15x is equal to negative 10. And when I multiply both sides by negative 1/15, we will get a result of x is equal to, let's see, 5 goes into 10 2 times and into 15 3 times, and a negative times a negative is positive. So x is 2/3. Okay, next up, second step, we will substitute x equals 2/3 into whichever equation you'd like. Let's do it into equation B. And this will enable us to solve for y. Okay. So here we go. Y equals negative 4x plus 2, that was our equation B, and we'll get y equals negative 4 times 2/3 plus 2. So what we did was using this x value, we plug that in. So we'll get y equals -8/3 plus 2, y equals -8/3, and I'm going to get a common denominator of 3. So we'll have -8/3 plus 6/3. So y will equal to -2/3. All right, so now our conclusion we got a solution of an ordered pair, 2/3, comma, -2/3. And this is a consistent system. All right, how'd you do? I bet it was fine. Don't worry, fractions are your friend. Okay, here we go. On with the lesson. Eliminating a variable using the addition method. This is also called the elimination method by some textbooks. So if you see that word, don't worry. It means the same thing. The addition method. Oops, sorry about that. The substitution method is most useful if one of the equations has an isolated variable. A third method for solving a linear system is the addition method. The addition method eliminates a variable by adding the equations. When we use the addition method, we want to obtain two equations whose sum is an equation containing only one variable. The key step is to obtain for one of the variables coefficients that differ only in sign. Steps for solving a system of two linear equations containing two variables by addition. So if necessary, rewrite both equations in the form ax plus by equals c, so standard form. If necessary, multiply either equation or both equations by appropriate non-zero numbers so that the sum of the x coefficients or y coefficients is 0. So we want to eliminate one of the variables. Then remember how we were talking about if you multiply both sides of a linear equation by a non-zero constant, you get an equation that represents the same line. So we can manipulate the way that the equation is written so that we can use it to eliminate one of the variables. Okay, so third step, add the equations. In step 2, the sum is an equation in one variable. And then solve the equation in one variable. Back substitute the value obtained in step 4 into either of the original equations and solve for the other variable. And then of course you should check the solution in both of the original equations. All right. Okay, so here we are. Example 1. Whoops, sorry, it was on 2 pages there. Solve the following systems of linear equations by the addition method. We want to state whether the system is consistent or inconsistent. For those systems that are consistent, state whether the equations are dependent or independent. Use set notation to express solution sets. So basically, systems will be consistent unless they get an answer that has no solution. So if you have parallel lines, which means you got an answer of no solution, that is an inconsistent system, and the equations are independent. The only systems who have dependent equations are the systems that are the same line. So those systems are the only ones that are dependent. So let's take a look at this first one. Okay. So again, it's useful to name the equations so we can see how we're manipulating them. So here we go. What would be the best variable to eliminate? If you looked at adding these exactly as it was, would one of the variables zero out? Good, you're right. One of the variables would indeed zero out. The y's would zero out. So if we, for our first step, if we were to take equation A plus equation B, this will eliminate y, and that will let us solve for x. So let's do it. We have x plus y equals 6. X minus y equals -2. So we're adding these equations, and you see we'll get 2x's plus 0y equals 4, which gives us 2x equal to 4 because 0y is 0. And then dividing both sides by 2, we get x is equal to 2. So we found one of our variables. So second step, substitute x equals 2 into which equation should we use? Equation A? Sounds good to me. Equation A. And this will enable us to solve for y. So here we go. Equation A was x plus y equals 6. But we got that x was 2. So if we subtract 2 from both sides, we'll get y is 4. So what we did was, that was when we got a result of x is 2. So we plugged it in there, and we solved for y. So let's go into our conclusion here. Conclusion. We got, oops, consistent in my colors. So we got the ordered pair 2, 4. We got an answer that was not the empty set. So it's a consistent system. And it's not, these equations are not multiples of each other. So we have independent equations. And we're all done. Okay? Okay, so now part B is a little bit more complicated. Okay, just a wee bit more. Because what we have is we have equation A and equation B, right? But none of the coefficients in front of the variables are opposites of each other, so we're going to have to adjust one or both of the two lines. So if you're looking at it, you see that if we wanted to eliminate the x's, we would have to multiply both equation A and equation B by numbers in order to get x totally eliminated. But if you look at the y's, if we eliminate the y's, we would only need to adjust equation A. So let's do that. If we were to start off by doing 5 times equation A plus equation B, this will eliminate the y's and we'll be able to solve for x. Okay? So here we go. 5 times A, right? So let's just look at 5 times A. That's 5 times 3x minus y, and we also have to do the 5 times the 11. Okay, so we're basically taking A and we're multiplying it by 5 on both sides of the equal sign. This is going to give us 15x's minus 5y's is equal to 55. Okay? So, let's put our new system into place. 15x minus 5y equals 55. And then we have equation B, which is 2x plus 5y equals 13. So when we add these, we're going to get 17x's plus 0y is equal to, let's see, 68. Okay. So we will have 17x, 0y is 0, so we'll just have 17x is equal to 68. And if we were to multiply both sides by 1/17, we will get 1x is equal to 68/17, which happens to be 4. Okay. All right. Second step, substitute x equals 4 into, why don't we do equation A, and this will enable us to solve for y. So equation A, before we had switched it, was 3x minus y equals 11. So substituting in x is 4, we'll have 3 times 4 minus y equals 11. 12 minus y is 11. Negative y, if I subtract 12 from both sides, would be negative 1. So y would be positive 1. So here's where we substituted in. And that's what we had found for x. All right, so now our conclusion. We got one ordered pair solution, 4, 1. So this is a consistent system. And it has independent equations. Okay. Comparing solution methods. So here's where we start, looking at the pros and cons of these methods. So the graphing method, you can see the solutions. So that's the good part about this guy. But the disadvantages, if the solutions do not involve integers or are too large or small to be seen on the graph, it's impossible to tell exactly what the solutions are. So that's the graphing method. Substitution method gives exact solutions. Easy to use if a variable is on one side by itself. Okay? Disadvantage. Solutions cannot be seen. Can introduce extensive work with your favorite fractions when no variable has a coefficient of 1 or -1. And the addition method, it gives exact solutions. It's easy to use, but your solutions cannot be seen. Okay. Okay. So now, so here we are in solving some of these systems. Actually, it looks like the first two, we're gonna, do you guys see that the first two are repeats of the ones that we just did? So I'll leave those to you guys if you want to drill yourself on them later. You can practice. Let's focus on C and D, all right, and go from there, or C, D, and E, and go from there. So here we go. I'm looking at C, and again, it's going to be easiest if we eliminate the Y. So I'm looking at this, and if we multiply, if we take A plus -2 times equation B, and this is my equation A and my equation B, this will eliminate the y's and we'll be able to solve for x, hopefully. Okay. So let's see what happens. So A is unchanged. Okay. And equation B, if I multiply that by -2 throughout, do you see I'll get -4x's plus 2y's equals -2. I multiplied each term by -2. And when I add that together, I get 0x's plus 0y's is equal to 0. 0 equals 0. What do you think? Weird one, huh? Is that true or false? It's true, right? So the good thing about it is we can jump straight to our conclusion. It means that these lines were multiples of each other, which means they're identical. So you get that kind of crazy solution where you say it's an ordered pair such that it's on one of the lines. So I'll just choose the first one, A, but you could have put either one. All right. Now, this system is consistent because we got a true answer. There's infinitely many solutions, infinitely many points on that line. So it's a consistent system, but it has dependent equations because they're the same line. Alrighty? Okay, and we'll look at the next one here. And we have to be careful because with this guy, notice we don't have it in standard form. So first step, I would go ahead and I would say, this is equation A, equation B. Rewrite equation A in standard form. So to do that, we just need to subtract 4y from both sides. So 3x minus 4y equals 1. Now we have our next step. How do we need to change these around? Good, we're going to need to change both of them around, aren't we? So why don't we go ahead and why don't we go ahead and eliminate the y's again, because we already have opposing signs on the y's. So if we were to multiply equation A by 3 and add 4 times equation B, we can eliminate y, and this will let us solve for x. Okay, so this is, my equation A in standard form. So if I triple that one, do you see that I'll get 12 x's, whoops, I'm going to stop me when I make up my own math, 9 x's minus 12 y's is equal to 3. Now I'm looking at equation B, and I'm going to multiply through by 4. So I'll get 16 x's minus plus 12 y's is equal to 4. And then when I add these guys, I'll get 25 x's plus 0 y's equals 7. Which gives a result of 25x is equal to 7. So x, when I multiply both sides by 1/25, will be 7/25. Okay. All right, so my next step, I'll come up here so I have enough room, will be substitute x equals 7/25 into equation, which one should we use? How about equation A? So equation A was 3x minus 4y equals 1, but x is 7/25. So I'll get this here. So this is what I plugged in for x. And this will give me 21/25 minus 4y's is equal to 1. I'll just get a common denominator. If I multiply 1 by 25 over 25, and then if I subtract that 21/25 from both sides, I will get negative 4y is equal to 25 minus 21 is 4/25. And then if I multiply both sides by negative 1/4, I will get a result of y is equal to the 4's divide out. Don't forget about that negative there. I'll have a negative 1/25. Okay, so my conclusion is I got a single intersection point of 7/25 comma negative 1/25, which makes this a consistent system with independent equations. Okay. All right, so our last one here. Last one, part E. So again, equation A and equation B. Let's eliminate the x's this time, just for the heck of it. All right, so I'm going to go ahead and if I multiply equation A times -3 and equation B times 2, I'll be able to eliminate the x's and solve for y. So -3 times equation A gives me -6x's minus 12y's equals -15. Each term got multiplied by -3. And then 2 times b, I'm doubling b, so I get 6x's plus 12y's is equal to 12. I think this might be another strange one. So this will give us 0x's plus 0y's is equal to -3. 0 equals -3. What do you guys think? True or false? False. Good. So we can go straight to our conclusion. If that means that there's no ordered pair that's on both of those lines. Okay. So we have no solutions at all, which means we have the empty set. This system is inconsistent because it doesn't have a solution. And it has independent equations because they're not the same line. Independent equations. Okay, so that wraps it up. That wraps it up for today. Have a wonderful rest of your day, and you'll be hearing from me soon. Bye.